Hello there. Tonight, you're not here to rush, not here to think too hard, not here to chase answers, but you're here to drift, to slow down, and to quietly step into one of the deepest, most powerful mysteries the universe has ever created: black holes. Not as something to fear, but as something to understand, because out there, far beyond the noise of everyday life, exist places where time itself begins to slow, where light fades into silence, and where reality bends in ways that feel almost impossible, yet perfectly natural. Massive stars live, burn, and collapse, leaving behind something so dense, so still, that not even light can escape its grip. And yet, despite all that power, there is no chaos and no sound and no rush, only silence and gravity doing their work. That I end this journey, you won't be pulled into panic. You'll be pulled into calm that will move slowly, truth by truth, uncovering 100 quiet, fascinating realities about black holes, how they form, how they shape galaxies, how they bend time, and how, in the end, even they begin to fade. This is not a story of destruction. It's a story of balance, of patience, of a universe that moves with quiet certainty. So, lower the lights, relax your mind, and let your thoughts drift. Because tonight, you're not just listening, you're falling gently into the darkest, calmest corners of the universe. Chapter 1. The Quiet Birth of Darkness. How black holes are formed. If you imagine the universe not as a violent explosion of chaos, but as something quieter, slower, almost like a deep, endless breath, then the birth of a black hole begins to make more sense. That it does not begin with darkness. It begins with light. Far out in the vastness of space, stars live long, patient lives. Some burn gently for billions of years, like steady candles in the night. But others, the truly massive ones, live fast and intensely, burning through their fuel with a kind of quiet urgency. These stars, often many times more massive than our own sun, are the ones destined to become black holes. Inside these stars, a delicate balance exists. Gravity is constantly trying to pull everything inward, compressing the star into itself. At the same time, nuclear fusion in the core pushes outward, creating energy and light. For millions of years, sometimes billions, this balance holds. But nothing in the universe lasts forever. Eventually, the star begins to run out of fuel. The nuclear reactions that once held gravity at bay begin to weaken. And when that happens, gravity, patient and relentless, finally takes over. This is where one of the most fascinating truths about black holes begins. A black hole is not something that suddenly appears. It is the result of a star losing its internal battle. As the core collapses under its own weight, temperatures rise dramatically. In mere seconds, the star's core can collapse faster than the speed of sound within the star itself. The outer layers, no longer supported, crash inward and then rebound violently, creating what we observe as a supernova explosion. For a brief moment, that dying star shines brighter than entire galaxies. And yet, at its center, something quieter is happening. The core continues collapsing. If the remaining mass is large enough, typically more than about 3 times the mass of the Sun, no known force in the universe can stop the collapse. Not electron pressure, not neutron pressure, nothing. And so the matter is compressed further and further and further still. This leads to another truth that feels almost impossible to grasp. A black hole forms when matter is compressed into an infinitely small point, known as a singularity. At this point, our understanding of physics begins to break down. Density becomes infinite. Space and time behave in ways we cannot fully describe. But before we even reach the singularity, something else forms first. An invisible boundary, calm, silent, and absolute. This is the event horizon. It marks the point beyond which nothing, not even light, can escape. Once this boundary forms, the collapsing core is effectively hidden from the rest of the universe. From the outside, all we see is darkness. And this brings us to another quiet but profound truth. Black holes are not empty voids. They are incredibly dense objects containing immense amounts of matter, compressed into a region so small that their gravity becomes overwhelming. To put this into perspective, imagine compressing the entire mass of the Earth into something the size of a marble. Now imagine doing that with something many times more massive than the Sun. The result is not just dense, it is extreme beyond everyday imagination. Yet, despite their dramatic origins, black holes themselves are surprisingly simple. They can be described using just a few properties: mass, spin, and electric charge. Everything else about the star that formed them, the elements, the structure, the history, is lost behind the event horizon. This leads to a strangely poetic idea. No matter how complex something once was, a black hole reduces it to simplicity. Another fascinating truth is that not all black holes are formed from dying stars. Some may have formed in the very early universe, just moments after the Big Bang. These are called primordial black holes, and while their existence is still being studied, they suggest that black holes could have been present almost since the beginning of time itself. There are also different sizes of black holes. Stellar mass black holes form from collapsing stars, typically ranging from a few times to dozens of times the mass of the Sun. But there are also supermassive black holes, millions or even billions of times more massive than the Sun, sitting quietly at the centers of galaxies. And here is another truth that feels almost surreal. Our own galaxy, the Milky Way, has a supermassive black hole at its center. It is called Sagittarius A*, and it influences the motion of stars across the galaxy, including, indirectly, our own solar system. Yet despite its immense power, it remains distant and calm, not the devouring monster often imagined in popular culture. Black holes do not roam the universe consuming everything in their path. They follow the same gravitational rules as any other object. If our Sun were suddenly replaced by a black hole of equal mass, Earth would continue orbiting in exactly the same way. The only difference would be the absence of light and warmth. This leads to one of the most calming truths about black holes. They are not cosmic predators chasing us through space. They are simply objects following the natural laws of the universe. And as you let that idea settle, there is something almost peaceful about it. These objects, born from the deaths of stars, are not chaotic anomalies. They are part of a larger story, a cycle of creation, transformation, and quiet persistence. Even in their formation, there is a strange kind of order. Stars live, stars die, and sometimes, in their final moments, they leave behind something that reshapes our understanding of reality itself. As you drift deeper into this thought, imagine that somewhere, far beyond what we can see, another massive star is reaching the end of its life right now. Its core is beginning to collapse. Its light will soon fade, and in its place, a new black hole will quietly form, adding to the vast, silent population already scattered across the universe. No sound, no announcement, just a shift from light into darkness. And yet, that darkness is not empty. It is full of mystery, waiting patiently to be understood. As the last light of a dying star fades into the vast background of space, what remains is not an ending, but a transformation so complete that it almost feels like a quiet reset of reality itself. One of the most intriguing truths about black hole formation is that, from a distance, the process appears to slow down dramatically. If you were watching a star collapse into a black hole from far away, you would never quite see the final moment. Instead, the surface of the collapsing star would seem to freeze just above the event horizon, growing dimmer and redder as its light stretches and weakens. This effect is caused by gravity's influence on time itself, a concept first described by Albert Einstein. Near extremely strong gravitational fields, time does not flow at the same rate as it does far away. This means that, in a sense, black holes form differently depending on where you are observing from. From the perspective of the collapsing star, the formation happens quickly, almost inevitably. But from the perspective of a distant observer, the process appears to stretch on, fading slowly into invisibility. This leads to a fascinating and slightly unsettling idea. Black holes are both formed and never fully formed, depending on how you look at them. Another remarkable truth is how little energy escapes the final stages of collapse compared to the earlier supernova explosion. Most of the visible drama happens before the black hole truly takes shape. Once the event horizon forms, the rest of the collapse is hidden forever. It becomes a private event in the universe, sealed off from observation. And yet, even though we cannot see black holes directly, we have learned to detect their presence through their effects on the surrounding environment. For instance, when matter falls toward a newly formed black hole, it does not always disappear immediately. Instead, it often forms a swirling disk of gas and dust, heated to extraordinary temperatures. This structure, known as an accretion disk, can glow brighter than entire star systems. From these glowing disks, we can infer the presence of something invisible at the center, something pulling everything inward with incredible force. Another subtle truth about black hole formation is that it is not always a solitary event. Many stars exist in binary systems, orbiting a companion star. When one of these stars collapses into a black hole, the system can continue to exist, now with one visible star and one invisible partner. Over time, the black hole may begin pulling material from its companion, creating a continuous flow of matter spiraling inward. This process can produce powerful X-ray emissions, which astronomers detect using space-based telescopes, and this way, black holes quietly reveal themselves, not through direct sight, but through influence. There is also a growing understanding that black holes may form through other pathways beyond single-star collapse. In dense regions of space, such as star clusters, repeated collisions and mergers between stars can lead to the gradual buildup of mass, eventually forming a black hole. And then there are the truly enormous ones, the supermassive black holes found at the centers of galaxies. Their origins remain one of the most compelling mysteries in astrophysics. Some theories suggest that they began as smaller black holes that grew over time, feeding on gas, stars, and even other black holes. Others propose that they may have formed directly from massive clouds of gas collapsing early in the universe, skipping the typical star phase entirely. What makes this even more fascinating is that these supermassive black holes seem to be deeply connected to the galaxies around them. There is a relationship between the mass of a galaxy and the mass of its central black hole, suggesting that they may grow together, influencing each other over billions of years. It is as if the black hole and the galaxy are engaged in a slow, silent conversation, shaping one another in ways we are only beginning to understand. Another truth that often surprises people is that black holes are not rare. In fact, scientists estimate that there may be millions of stellar mass black holes in our galaxy alone. Most of them are completely invisible, drifting quietly through space without interacting with anything around them. This means that the universe is far more populated with black holes than we might expect. They are not exceptional anomalies, but rather a natural outcome of how stars evolve. And yet, despite their abundance, each black hole represents an extreme limit of physics, a place where our current theories begin to stretch and blur. There is also a gentle irony in how black holes are named. The term itself suggests emptiness, a kind of absence. But in reality, they are anything but empty. They are regions of space where matter and energy have been compressed to such an extent that they dominate their surroundings completely. Even their darkness is not truly a lack of existence, but rather a consequence of gravity being so strong that light cannot escape. As you continue to reflect on this, another calming realization begins to emerge. Black holes do not disrupt the overall harmony of the universe. They are part of it, woven into its structure, contributing to its evolution. The elements created in stars, the same elements that make up planets, oceans, and even living beings, are scattered across space when stars explode. Some of that material may eventually fall into black holes, while other parts go on to form new stars and worlds. In this way, black holes are connected to the broader cycle of cosmic life. There is also something deeply quiet about the way black holes exist after their formation. Once created, they do not shine or flicker like stars. They simply persist, steady and unchanging, unless something comes close enough to be drawn in. This stillness can feel almost meditative when you think about it. In a universe full of motion and energy, black holes represent a kind of calm center, a place where everything slows down, where light itself comes to rest. And yet, even in this stillness, they continue to shape the universe around them. Stars orbit them. Gas clouds drift toward them. Entire galaxies are influenced by their presence. All of this happens without noise, without spectacle. Just the quiet pull of gravity doing its work. As you settle into this thought, imagine the countless black holes scattered across the universe, each one born from the life of a star, each one carrying within it a story that can no longer be seen. They are like silent archives of cosmic history, holding within them the remnants of what once was, hidden beyond a boundary we cannot cross. And perhaps that is what makes them so captivating. Not just their power or their mystery, but the way they quietly remind us that the universe is deeper than what we can observe, and calmer than what we often imagine. Even in the most extreme conditions, there is a kind of order, a rhythm, a flow. Stars ignite, burn, and fade. Black holes form, persist, and wait. And through it all, the universe continues vast, steady, and almost gently indifferent. As your thoughts begin to slow, you might find comfort in that idea, that even the most dramatic transformations in the cosmos happen in silence. No rush, no urgency, just time stretching endlessly onward, carrying with it the quiet birth of darkness. Chapter 2: The Edge of No Return. Understanding event horizons. There is a boundary in the universe that cannot be seen, cannot be touched, and yet defines one of the most absolute limits in all of physics. It does not glow. It does not shimmer. It does not announce itself in any dramatic way. And still, it is one of the most important thresholds that exists anywhere in space. This boundary is known as the event horizon. To understand it, you don't need to imagine something complex or chaotic. Instead, imagine something simple, a point of no return, a place where once you cross, there is no path back. No matter how fast you travel or how strong you are. One of the most calming yet profound truths about the event horizon is that it is not a physical surface. If you could approach it, there would be no wall, no sudden impact, no visible line in space. You could pass through it without even realizing the exact moment it happened. And yet, crossing it would change everything. The event horizon marks the distance from a black hole at which the escape velocity becomes equal to the speed of light. This idea traces back to early insights from John Michel, who imagined objects so massive that even light could not escape their pull. But it was much later, through the work of Carl Schwarzschild, that the exact mathematical description of this boundary was found. His solution to Einstein's equations revealed a specific radius, now called the Schwarzschild radius, where this point of no return exists. And this leads to a fascinating truth. The size of a black hole's event horizon depends only on its mass. If the sun were somehow compressed into a black hole, its event horizon would be only about 3 kilometers wide. Something so massive, reduced to such a small boundary, feels almost unreal. Yet, this is how gravity behaves at its most extreme. As you imagine approaching this invisible boundary, something else begins to happen, something subtle but deeply important. Time itself begins to change. According to the theory of relativity, first introduced by Albert Einstein, gravity affects the flow of time. The stronger the gravitational field, the slower time moves relative to an outside observer. Near the event horizon, this effect becomes incredibly strong. Someone far away, watching an object fall toward a black hole, it would appear to slow down more and more as it gets closer to the event horizon. Its movements would stretch out, becoming slower and dimmer, as if time itself were gently fading. Eventually, the object would seem to freeze at the edge, never quite crossing over. But this is only an illusion from the outside. From the perspective of the object itself, time continues normally. It would cross the event horizon in a finite amount of time, without noticing anything particularly special at that exact moment. This creates one of the most intriguing dual realities in physics. Two observers can witness completely different versions of the same event, both equally valid. Another quiet truth about the event horizon is how it shapes the way we understand information. Anything that crosses the event horizon becomes permanently hidden from the outside universe. No signal, no message, no light can escape to tell us what happens beyond that point. This raises a deeply fascinating question. If information cannot escape, is it lost forever? This question has puzzled scientists for decades and leads into one of the greatest mysteries in modern physics. But for now, it is enough to sit with the idea that the event horizon is not just a boundary of space, but a boundary of knowledge. There is also something strangely peaceful about how absolute this boundary is. In everyday life, most limits can be challenged, pushed, or overcome. But the event horizon is different. It is a limit set by the fundamental structure of the universe itself. There is no technology, no force, no clever method that allows something to escape once it has crossed this threshold. And yet, this absolute nature does not feel violent. It feels quiet. The event horizon does not pull things in like a vacuum. Objects must come close enough, drawn by gravity, before they reach it. From a distance, a black hole behaves just like any other object with the same mass. This leads to another calming truth. Space is vast, and black holes are not actively hunting anything. The event horizon simply exists, waiting. It is up to matter and energy to wander close enough to be affected. As you imagine this boundary, it helps to think of it not as a destructive force, but as a transition. A place where the familiar rules of the universe give way to something deeper and less understood. Even light, the fastest thing in the universe, cannot escape once it passes this point. This is what makes black holes truly black. They do not emit or reflect light from within the event horizon. But just outside this boundary, the story becomes more complex. Light can orbit a black hole at a certain distance, creating what is known as a photon sphere. Here, gravity is so strong that light can bend into circular paths, looping around the black hole before either escaping or falling inward. This creates a kind of glowing ring around the darkness, a visual hint of the boundary that lies just beyond. And in 2019, humanity captured its first image of a black hole's shadow, revealing this glowing ring around the event horizon. It was not a direct image of the black hole itself, but rather the light from the surrounding matter, bent and shaped by extreme gravity. This image came from the Event Horizon Telescope, a global network of radio telescopes working together to observe something that cannot be seen directly. And perhaps that is what makes the event horizon so captivating. It is not something we can observe in the traditional sense. It does not emit signals or reflect light. And yet, through careful observation and understanding, we can infer its presence and study its properties. Another subtle truth is that the event horizon is not fixed in place like a solid object. If a black hole gains mass, its event horizon expands. If it loses mass, through processes we will explore later, it can shrink. This means that the boundary itself is dynamic, changing over time as the black hole evolves. And still, despite all these complexities, the event horizon remains elegantly simple in its definition. The point beyond which nothing returns. As your thoughts begin to slow, imagine drifting closer to this invisible edge, not in fear, but in curiosity. There is no sudden change in texture or temperature, no dramatic signal, just a quiet crossing from one region of the universe into another. And beyond that boundary, everything continues, but in ways we cannot fully see or understand. There is something deeply calming about that mystery, a reminder that not everything needs to be known all at once. Some things, like the event horizon, simply exist, quietly marking the edge of what we can understand. As you continue to imagine this invisible boundary, something subtle begins to settle in, the realization that the event horizon is not just a limit in space, but a quiet turning point in how reality behaves. One of the most fascinating truths about the event horizon is that it does not act like a surface in the way we experience surfaces in everyday life. There is no resistance, no texture, no sensation that tells you that you've reached it. If you were drifting toward it, you would not feel a sudden pull or a dramatic shift at the exact moment you crossed. And yet, everything beyond that moment becomes permanently hidden from the universe you came from. This leads to another deeply intriguing idea. The event horizon is less like a wall and more like a one-way direction in time. Once crossed, all possible paths, every future moment, lead deeper inward. There is no path that leads back out. In this sense, falling into a black hole is not just a movement through space, but a movement toward a future that cannot be reversed. Another quiet truth is that the event horizon behaves differently depending on the size of the black hole. For smaller black holes, especially those formed from collapsing stars, the gravitational difference between your head and your feet, what scientists call tidal forces, can become extreme even before reaching the event horizon. This effect is often described in a vivid but simple way. As you approach, gravity pulls more strongly on the part of you closer to the black hole than the part farther away, stretching you into a long, thin shape. This process has been informally named spaghettification. But here's where things become unexpectedly calm again. For supermassive black holes, those millions or billions of times more massive than the Sun, the event horizon is much larger and the tidal forces at the boundary can be surprisingly gentle. In fact, you could cross the event horizon of such a black hole without experiencing any noticeable stretching at that moment. The real effects would come later, deeper inside. This contrast reveals another truth. Not all black holes are equally intense at their edges. The experience of approaching one depends greatly on its size. There is also a subtle relationship between the event horizon and temperature, something that seems almost contradictory at first. Black holes are often thought of as cold, dark objects. But in the 1970s, a remarkable idea was proposed by Stephen Hawking, suggesting that black holes are not completely black. Due to quantum effects near the event horizon, they can emit a very faint form of radiation, now known as Hawking radiation. This means that the event horizon is not entirely silent. At an incredibly subtle level, it is involved in processes that slowly release energy back into the universe. The temperature associated with this radiation is extremely low for large black holes, far colder than the cosmic background of space itself. But for smaller black holes, the temperature increases, making them more active in this quiet quantum sense. This introduces a gentle paradox. The boundary that traps everything also participates in a process that allows energy to escape, though in a very different form. Another fascinating truth is how the event horizon relates to information. In physics, information is not just about knowledge or data. It refers to the fundamental details that describe a system. When something crosses the event horizon, all of that information seems to disappear from the observable universe. This creates a deep puzzle. If information is truly lost, it would violate the laws of quantum mechanics, which suggest that information must always be preserved in some form. This problem, often referred to as the black hole information paradox, has led to decades of research and debate. Some theories suggest that the information is somehow encoded on the surface of the event horizon itself, like a kind of cosmic memory. Others propose that the information is gradually released through Hawking radiation, though in a highly scrambled form. There is even a more abstract idea known as the holographic principle, which suggests that everything inside a volume of space can be described by information on its boundary, in this case, the event horizon. While these ideas are still being explored, they reveal something profound. The event horizon may not just be a boundary in space, but a place where the deepest rules of reality intersect. And yet, despite all this complexity, the event horizon remains remarkably consistent in its role. It is always the point beyond which signals cannot return. It is always the limit of escape. And it is always defined by the same fundamental relationship between mass and gravity. Another quiet truth is that event horizons are not unique to black holes alone. Similar concepts appear in other areas of physics and cosmology. For example, the observable universe itself has a kind of horizon, the distance beyond which light has not had enough time to reach us since the beginning of the universe. In this way, the idea of a boundary beyond which we cannot see or know is woven into the very structure of reality. It is not something to be feared, but something to be understood. As you continue to reflect, imagine the countless event horizons scattered across the universe, each one marking a place where the known transitions into the unknown. They do not move aggressively or expand suddenly. They grow or shrink slowly in response to the changes in their black holes. They exist quietly, like still points in a vast and ever-changing cosmos. There is something deeply calming in that image, and no chaos, no urgency, just boundaries gently defining the limits of what can be observed. And perhaps that is what makes the event horizon so meaningful. It reminds us that the universe is not just about what we can see, but also about what lies just beyond our reach. Not everything is meant to be fully observed. Some things remain hidden not out of hostility, but out of the natural structure of existence itself. As your thoughts drift, you might begin to feel that the event horizon is not just a scientific concept, but a quiet metaphor. A reminder that every boundary, every edge, is also a place of transition. A place where one form of understanding ends and another begins. And in that gentle shift, there is no need for fear, only curiosity, only calm, only the quiet awareness that the universe is far deeper than it first appears. Chapter 3: Inside the Unknown. What lies beyond the singularity? There is a point at the heart of every black hole where our understanding begins to soften, where the equations that describe the universe so precisely everywhere else begin to lose their clarity. It is not loud or explosive. It does not announce itself with light or motion, and yet it represents one of the deepest mysteries that exists anywhere in reality. This point is called the singularity. If the event horizon is the boundary we cannot return from, the singularity is what lies at the center of that journey, a place where everything that has crossed the horizon is thought to gather, compressed into a region so small that it challenges the very language of physics. One of the most striking truths about the singularity is that it is not something we can directly observe, not even in principle. All information about it is hidden behind the event horizon. What we know about it comes from theory, from mathematics, and from the quiet consistency of physical laws as they extend toward their limits. And as those laws are extended, something unusual happens. They begin to break. The equations derived from Albert Einstein's general theory of relativity predict that, under extreme gravitational collapse, matter is compressed into a point of infinite density and zero volume. In this description, space and time themselves curve inward without limit. But infinity in physics is often a sign not of something literal, but of something incomplete. It suggests that our current understanding is reaching beyond its range, like a map that simply stops at the edge of the known world. This leads to a quiet but important realization. The singularity may not truly be a point of infinite density. Instead, it may represent a place where a deeper, more complete theory of nature is required, one that combines gravity with the principles of quantum mechanics. This is where the search for a theory of quantum gravity begins. Another fascinating truth is that, as you move closer to the singularity, at least in theory, space and time begin to behave in ways that are almost impossible to visualize in everyday experience. Time moves forward, steadily and predictably. Space has dimensions we can navigate: left, right, forward, backward. But near a singularity, these roles begin to shift. Inside a black hole, once past the event horizon, moving toward the singularity becomes as inevitable as moving forward in time. Just as you cannot choose to stop time or reverse it, you cannot choose to avoid the singularity once you are inside. This creates a deeply unusual idea. Within a black hole, the singularity is not just a place in space, it is part of your future. Every path leads toward it. Another quiet truth is that the structure of the singularity may not be as simple as a single point. Some solutions to Einstein's equations suggest that, depending on the rotation of the black hole, the singularity could take on different shapes. For a non-rotating black hole, it is often described as a point. But for a rotating black hole, known as a Kerr black hole, the singularity may form a ring-like structure. This ring singularity opens the door to even more speculative ideas. Some theoretical models suggest that such structures could connect to other regions of spacetime, forming what are known as wormholes. These are hypothetical passages that could link distant parts of the universe, or perhaps even different universes entirely. While there is no experimental evidence for wormholes, their existence arises naturally from certain solutions in general relativity, making them a subject of ongoing curiosity. And yet, even as these ideas expand into the imaginative, the core truth remains grounded. We do not yet know what truly lies at the center of a black hole. Another subtle and fascinating point is that the singularity represents a place where known forces converge. Gravity becomes overwhelmingly dominant, compressing matter to extreme densities. At the same time, quantum effects, usually significant only at very small scales, are expected to become important as well. But these two frameworks, general relativity and quantum mechanics, do not yet fully agree with each other. This creates a kind of quiet tension in physics, where two highly successful theories describe different aspects of reality, but cannot yet be fully combined. The singularity sits at the center of this tension, waiting to be understood. There is also something deeply poetic about the idea of the singularity. Everything that falls into a black hole, stars, gas, light, perhaps even entire systems, is thought to contribute to this central region. It becomes a place where histories merge, where individual identities are lost, and where complexity is reduced to something fundamentally simple. And yet, that simplicity is only apparent in truth. It may be one of the most complex and information-rich regions in the universe, hidden beyond a boundary we cannot cross. Another truth that often goes unnoticed is how the singularity challenges our sense of scale. In everyday life, we think of size and distance as meaningful concepts. But at the singularity, these ideas lose their usual meaning. When something is described as having zero volume, it no longer fits within the framework of space as we understand it. This leads to a quiet question. If something occupies no space, how do we describe where it is? And perhaps the answer is that our usual concepts of where no longer apply. As you continue to reflect, it becomes clear that the singularity is not just a physical concept. It is a boundary of understanding. It marks the point where our current knowledge reaches its limit. But rather than being frustrating, there is something calming about this limit. It reminds us that the universe is not something we have fully solved or completed. It is still unfolding, still offering new questions, still inviting deeper exploration. Even the most advanced theories we have are part of an ongoing journey. And at the center of that journey, quietly and patiently, sits the singularity. Unseen, unreachable, and yet deeply connected to everything around it. As your thoughts begin to slow, imagine this hidden center, not as something chaotic or threatening, but as something still, something beyond the need for motion or change. A place where the familiar dissolves and something entirely different takes its place. Not in a dramatic way, but in a quiet, almost gentle shift from what we know into what we are still learning to understand. As you continue to drift deeper into this idea of the singularity, it begins to feel less like a destination and more like a quiet boundary, one that does not separate places but separates understanding. What makes the singularity so uniquely fascinating is not just what it might be, but how it challenges everything we assume about reality. It is not simply another object in space. It is a place where the very concepts of space and time begin to lose their familiar meaning. One of the most important truths to gently settle into is this: our current theories do not fully describe what happens at the singularity. General relativity, developed by Albert Einstein, tells us how gravity shapes the universe on large scales. It explains the motion of planets, the bending of light, and the expansion of the cosmos. And when applied to black holes, it predicts the formation of a singularity, a point where curvature becomes infinite. But quantum mechanics, the theory that governs the smallest scales of reality, tells a very different story about how nature behaves. And when these two theories are brought together near a singularity, they do not align. This mismatch is not a failure, but rather a quiet signal that something deeper is waiting to be discovered. Scientists have been working for decades to find theory that unifies these two frameworks, a theory of quantum gravity. And within these efforts, new ideas begin to emerge. One such idea suggests that the singularity may not be infinitely small after all. Instead, it could be replaced by an extremely dense but finite structure, sometimes referred to as a Planck scale core. At this scale, far smaller than anything we can currently observe, quantum effects might prevent the collapse from continuing indefinitely. In this view, the singularity is not a point of infinite density, but rather a region where matter is compressed to the highest possible limit allowed by the laws of physics. Another fascinating possibility comes from loop quantum gravity, a theory that attempts to describe space itself as made of tiny, discrete units. In some models, this leads to the idea that the collapse of a black hole could eventually reverse, creating what is known as a white hole. A white hole is, in a sense, the opposite of a black hole. Instead of pulling matter inward, it would release matter outward. While no white holes have been observed, the idea offers a gentle suggestion that even the most extreme collapse might not be the final step in the story. There are also proposals within string theory, another approach to quantum gravity, that suggests the singularity could be replaced by a complex structure of vibrating strings or higher dimensional objects. These ideas are still highly theoretical, but they share a common theme. The singularity may not be the end of physics, but rather the beginning of a deeper layer of it. Another quiet truth about the singularity is how it reshapes our understanding of cause and effect. Outside a black hole, events unfold in a sequence we can follow. Causes lead to effects. Time flows in a direction we recognize. But near the singularity, these relationships become less clear. Because all paths inside the event horizon lead toward the singularity, it becomes difficult to define before and after in the usual sense. The singularity is not just in the future, it defines the future. This creates a kind of stillness in the concept of time itself. Everything moves toward the same conclusion, not through choice or chance, but through the structure of space-time. And yet, despite this inevitability, there is no sense of urgency in the process. From the perspective of an outside observer, everything slows down as it approaches the event horizon. From the inside, the journey continues steadily, without sudden changes at the boundary. This duality adds to the quiet mystery of the singularity. Another subtle and often overlooked truth is that singularities are not exclusive to black holes. According to our current models, the universe itself may have begun as a kind of singularity during the Big Bang. At that moment, all of space, time, matter, and energy were compressed into an extremely dense state, from which everything expanded. This parallel suggests something deeply interesting. The same kind of extreme conditions that exist at the center of black holes may also have existed at the very beginning of the universe. In a way, singularities connect the largest scales of existence. With the smallest, they appear at both the beginning of time and within some of its most extreme objects, and yet, in both cases, they remain beyond direct observation. There is also a quiet elegance in how the singularity simplifies everything that falls into it, no matter how complex an object may be. A star with layers of elements, a cloud of gas with intricate motion, or even light carrying information from distant regions. Once it crosses the event horizon and moves toward the singularity, all of that complexity is reduced. What remains is something that can be described only in the most basic terms. Massachusetts. Spin. Charge. This simplicity is not a loss in a negative sense, but a transformation into a more fundamental state. And perhaps that is what makes the singularity feel less like an ending and more like a quiet convergence. A place where differences dissolve and everything becomes part of a deeper unity. As your thoughts continue to soften, imagine the singularity not as something sharp or violent, but as something still and silent. A place where motion ceases to have meaning, where direction becomes irrelevant, where the familiar structure of reality gently fades. There is no need to fully understand it. In fact, part of its nature is that it cannot yet be fully understood. And that is perfectly okay. Because the singularity does not demand answers. It simply exists at the edge of what we know. A quiet reminder that the universe is not limited to what we can currently explain. There are depths beyond our theories, spaces beyond our equations, and at the center of it all, there are mysteries that remain patient, waiting for us to approach them with curiosity rather than certainty. As you settle into this idea, there is something almost comforting about it. The realization that not everything needs to be resolved, that some parts of the universe are meant to remain open questions, not as gaps, but as invitations. And somewhere, far beyond what we can see, at the center of countless black holes scattered across the cosmos, these singularities continue to exist, silent, hidden, unchanging, holding within them the quiet promise that there is always more to discover. Chapter 4: The Slow Dance of Gravity. How black holes shape galaxies. If you step back, far beyond individual stars, beyond nebulae and clusters, and begin to see galaxies as whole, slow-moving systems, a quieter truth begins to emerge. Galaxies are not random gatherings of stars drifting without purpose. They are structured, balanced, and gently shaped over billions of years by something deeply influential at their centers. And at the heart of nearly every large galaxy, including our own Milky Way, there rests a black hole. Not a small one, not a remnant of a single star, but something far more immense, what we call a supermassive black hole. These black holes can contain millions or even billions of times the mass of our Sun. And yet, despite their size, they do not dominate their galaxies in an aggressive or chaotic way. Instead, they participate in something more subtle, a slow dance of gravity that shapes the structure of everything around them. One of the most fascinating truths is that these central black holes are deeply connected to their host galaxies. Observations have shown a consistent relationship between the mass of a galaxy's central black hole and the size of the galaxy's bulge, the dense region of stars near its center. This relationship suggests that black holes and galaxies do not evolve separately. They grow together, influencing one another across immense stretches of time. At the center of the Milky Way lies a supermassive black hole known as Sagittarius A star. It is relatively quiet compared to others, not actively consuming large amounts of matter. And yet, its presence shapes the orbits of stars in the galactic core. Astronomers have observed stars moving in tight, fast orbits around this invisible center, providing strong evidence of its existence. These stars trace out paths that reveal the immense gravitational pull of something we cannot see directly. And still, the motion is not chaotic. It is precise, predictable, almost graceful. This brings us to another calming truth. Gravity, even at its most powerful, often creates order rather than disorder. Black holes, especially supermassive ones, act as anchors within galaxies. They help stabilize the motion of stars and influence the distribution of matter. Over time, this contributes to the overall shape and structure of the galaxy itself. But their influence extends beyond simple gravitational pull. When a black hole actively feeds, drawing in gas, dust, and even stars, it can release enormous amounts of energy in the process. This energy does not come from the black hole itself, but from the material as it spirals inward, heating up and emitting radiation in some galaxies. This process creates what are known as active galactic nuclei or quasars, extremely bright regions at the centers of galaxies that can outshine the combined light of billions of stars. These luminous cores are powered by black holes consuming matter. And yet, even this intense activity plays a role in shaping galaxies in a balanced way. The energy released can push gas away from the center, regulating the rate at which new stars form. Without this feedback, galaxies might form stars too quickly, using up their material in a short time. So, in a quiet and indirect way, black holes help control the life cycle of galaxies. They are not just consumers, they are regulators. Another fascinating truth is that galaxies themselves are not static. They move, interact, and sometimes even merge with one another. When two galaxies collide, their central black holes begin a slow approach, drawn together by gravity over time, sometimes hundreds of millions of years. These black holes spiral closer and eventually merge, forming an even larger black hole. This process releases powerful ripples through space-time, known as gravitational waves, subtle disturbances that travel across the universe. Even in these moments of cosmic change, there is no sudden violence in the way we might imagine. The timescales are so vast that everything unfolds slowly, almost gently, on a human scale of perception. Another quiet truth is that the presence of a black hole does not necessarily mean constant activity. Many supermassive black holes, including Sagittarius A*, spend long periods in a dormant state with very little matter falling into them. During these times, they are nearly invisible, influencing their surroundings primarily through gravity alone. This stillness is an important part of their nature. They do not need to be active to be significant. Even in silence, they shape the paths of stars, guide the motion of gas clouds, and contribute to the overall stability of the galaxy. There is also a broader pattern that begins to emerge when we look across the universe. Almost every large galaxy we observe appears to host a supermassive black hole at its center. This consistency suggests that black holes are not rare exceptions, but fundamental components of galactic structure. It is as if the formation of a galaxy and the formation of its central black hole are deeply linked processes, two aspects of the same cosmic story. Another subtle truth is how black holes influence the distribution of dark matter, the invisible substance that makes up much of the universe's mass. While dark matter does not interact with light, it responds to gravity. The presence of a supermassive black hole can affect the way dark matter is distributed near the center of a galaxy, contributing to the overall gravitational landscape. And yet, even with all these interactions, the scale of a galaxy is so vast that the black hole occupies only a tiny region at its center. This creates a gentle contrast. Something incredibly small, relative to the galaxy, having a profound influence on something incredibly large. It is a reminder that size and impact are not always directly connected. As your thoughts begin to slow, imagine the galaxy not as a chaotic swirl of stars, but as a quiet system, moving in harmony over billions of years. At its center, the black hole does not shout or demand attention. It simply exists, steady, patient, guiding the motion of everything around it through the quiet force of gravity. Stars orbit, gas flows, light travels, and at the heart of it all, unseen but ever present, the black hole continues its slow, silent dance, shaping the galaxy in ways that are both subtle and profound. As you continue to imagine a galaxy drifting through the vastness of space, its billions of stars moving in quiet harmony, something deeper begins to emerge. The influence of a black hole is not just about gravity pulling inward. It is also about balance, timing, and the gentle regulation of cosmic growth. One of the most fascinating truths is that black holes can shape galaxies not only by what they pull in, but by what they push away. When matter spirals toward a supermassive black hole, it forms a hot, luminous disk, and in many cases, powerful jets of energy are launched outward from the region near the black hole. These jets can travel across enormous distances, sometimes extending far beyond the galaxy itself. They move at speeds close to that of light, carrying energy into the surrounding space. But instead of creating chaos, these jets often help maintain balance within the galaxy as they push gas away from the central regions. They can prevent too much matter from collapsing into new stars all at once. This process is known as feedback, and it plays a crucial role in controlling star formation. Without it, galaxies might burn through their material quickly, creating stars in rapid bursts and then fading prematurely. With it, star formation becomes more gradual, allowing galaxies to evolve over billions of years in a more stable way. This reveals another quiet truth. Black holes do not simply consume, they also help sustain. There is also something deeply calming in the way galaxies evolve over time. Even when galaxies collide, the process is not the kind of sudden crash we might imagine. Stars are so far apart that direct collisions between them are extremely rare. Instead, the galaxies pass through one another, their shapes stretching and reshaping over time. During these interactions, their central black holes begin a slow approach, drawn together by gravity. Eventually, they form a binary system, two black holes orbiting each other in a gradually tightening spiral. Over immense periods of time, they lose energy through gravitational waves, inching closer until they finally merge. This merging process releases an enormous amount of energy in the form of ripples in spacetime, but even this happens over a timescale that feels almost still when compared to human experience. Another fascinating truth is that these mergers can slightly shift the position of the resulting black hole. In some cases, the newly formed black hole can receive a kick from the asymmetry of the merger, causing it to move away from the exact center of the galaxy. Over time, gravity pulls it back toward the center, restoring the balance. This gentle correction reflects the stability of the system as a whole. There is also a growing understanding that black holes may influence not just the centers of galaxies, but their outer regions as well. Through their feedback processes, They can affect the temperature and movement of gas far beyond their immediate surroundings. This, in turn, influences how galaxies grow, how they form stars, and how they interact with nearby galaxies. Another subtle truth is that galaxies without active black holes tend to behave differently from those with active ones. In galaxies where the central black hole is actively feeding, the energy output can be so significant that it shapes the entire galaxy's appearance and evolution. In contrast, galaxies with quiet black holes may evolve more slowly, with fewer dramatic changes. This variation adds to the diversity we observe across the universe. And yet, despite these differences, the underlying presence of a central black hole remains a common thread. It is as if black holes provide a kind of foundation, a central point around which the rest of the galaxy organizes itself. There is also something deeply interconnected about this relationship. The matter that feeds a black hole often comes from the same gas clouds that form stars. In this way, star formation and black hole growth are linked processes, each influencing the other. When a galaxy has abundant gas, both star formation and black hole feeding can increase. When the gas is depleted, both processes slow down. This shared resource creates a natural balance between growth and stability. Another quiet truth is that even though black holes are incredibly dense and powerful, their influence diminishes with distance, just like any other gravitational object. Far from the center of a galaxy, stars orbit in ways that are influenced more by the combined mass of all the stars and dark matter than by the black hole itself. This creates a layered structure of influence where different forces dominate at different scales. And yet, the central black hole remains a key part of the overall system. There is also a sense of rhythm in how galaxies evolve. Periods of activity when the black hole is feeding and releasing energy are followed by periods of calm, where little changes over long stretches of time. This cycle can repeat over billions of years, creating a dynamic yet stable environment. As you settle into this idea, it becomes clear that black holes are not isolated phenomena. They are deeply integrated into the fabric of the universe, connected to the formation and evolution of galaxies on the largest scales. They do not act alone. They are part of a larger system, contributing to the slow unfolding of cosmic structure. And perhaps that is what makes their role so calming. Despite their extreme nature, they do not disrupt the universe. They help shape it gently, steadily, over time. As your thoughts begin to drift, imagine looking out across the universe, not as a collection of separate objects, but as a vast network of galaxies, each one with its own center, its own quiet anchor. Within each of these galaxies, a black hole sits silently, guiding the motion of stars, influencing the flow of gas, and participating in the long, slow story of cosmic evolution. There is no rush in this process and no urgency, just time, stretching across billions of years, allowing galaxies to form, change, and settle into their shapes. And at the heart of it, all the black holes remain, steady, unseen, and essential. A quiet presence in a universe that moves slowly enough to feel almost still. Chapter 5: Time, Light, and Illusion. Relativity near a black hole. There is something deeply calming about the idea that time is not as fixed as it feels. In everyday life, time seems steady and reliable. Seconds pass one after another, moments unfold in a familiar rhythm, and everything appears to move forward at the same pace. But as you move closer to a black hole, this quiet certainty begins to soften, and something far more fluid takes its place. One of the most profound truths about black holes is not just what they do to space, but what they do to time itself. This idea comes from the work of Albert Einstein, whose theory of relativity revealed that time is not absolute. It can stretch, slow down, and even differ between observers depending on gravity and motion. Near a black hole, this effect becomes incredibly strong. Imagine drifting closer to a black hole, far enough away that you are still safe, but close enough to feel its influence. If someone were watching you from a great distance, far from the black hole, they would notice something unusual. To them, your movements would begin to slow down. Your clock would tick more slowly. Your actions would stretch out in time. Even your voice, if it could be heard, would deepen and fade as the light carrying it loses energy. This is known as gravitational time dilation. The stronger the gravity, the slower time passes relative to an outside observer. And near a black hole, gravity becomes so intense that this effect is no longer subtle. It becomes dominant that as you approach the event horizon, time appears to slow down more and more from the outside perspective. Eventually, it would seem as though you are almost frozen in place, hovering just above the edge, your image becoming dimmer and redder as the light struggles to escape. But here is where the quiet beauty of relativity reveals itself. From your own perspective, nothing feels unusual about time. Your heartbeat remains steady. Your thoughts flow normally. You would cross the event horizon in a finite amount of your own time without noticing any dramatic pause or freeze. This creates one of the most fascinating dual experiences in the universe. Two observers witnessing the same event in completely different ways. Another subtle truth is that this effect is not unique to black holes. Time dilation occurs anywhere there is gravity, even on Earth. The difference is extremely small here, but it has been measured with precise instruments. Clocks placed at higher altitudes where gravity is slightly weaker tick just a tiny bit faster than those at sea level. Near a black hole, the same effect becomes profound. Time stretches so much that what feels like minutes to you could correspond to years or even longer for someone far away. This leads to a deeply thought-provoking idea. Black holes can act as natural time machines in a very specific sense. Not machines that allow you to travel backward in time, but environments where time passes at different rates, creating a separation between experiences. If you could somehow approach a black hole safely and then return, you might find that much more time has passed in the universe than you experienced personally. This is not science fiction. It is a direct consequence of relativity. Another fascinating truth is how light behaves in these extreme conditions. Light always travels at the same speed locally, but its energy and wavelength can change depending on gravity. As light climbs away from a strong gravitational field, it loses energy and shifts toward longer wavelengths, a process known as gravitational redshift. Near a black hole, this effect becomes very strong. Light emitted from near the event horizon appears stretched and dim when observed from far away. Colors shift toward red, then infrared, and eventually beyond what human eyes can detect. This contributes to the fading appearance of objects as they approach the event horizon. There is also a beautiful symmetry in how light behaves around black holes. While some light escapes, much of it is bent by the intense gravity, curving around the black hole in graceful arcs. This bending of light, known as gravitational lensing, can create distorted and magnified images of objects behind the black hole. In some cases, light can even loop around the black hole multiple times before escaping, creating multiple images of the same object. This gives rise to a kind of cosmic illusion, where what you see is not a direct path, but a journey shaped by gravity itself. Another quiet truth is that near a black hole, the distinction between space and time begins to blur. In everyday experience, space and time feel like separate things. You move through space while time moves forward. But in the framework of relativity, they are part of a single structure called space-time. And near a black hole, this structure becomes deeply curved. Paths that would normally be straight become curved. Directions that seem separate begin to mix, and the idea of a straight line loses its usual meaning. This curvature is not something you would feel directly, but it shapes everything around you: how objects move, how light travels, and how time flows. Another fascinating aspect is how these effects create a kind of visual distortion. If you were near a black hole, the sky would not look as it does from Earth. Stars would appear shifted, stretched, and sometimes duplicated due to the bending of light. The black hole itself would appear as a dark region surrounded by a bright, glowing ring, the result of light being trapped and redirected. This is not chaos, but a different kind of order, one governed by the geometry of space-time that as your thoughts begin to slow. There is something deeply calming about this perspective. Time is not rigid, light is not always straight. Reality is not fixed in a single, unchanging form. Instead, everything is flexible, shaped by gravity, motion, and perspective. And near a black hole, these hidden aspects of the universe become visible in the most gentle and profound ways. What once seemed absolute begins to soften. What once felt certain becomes open to interpretation. And in that quiet shift, there is a sense of wonder, not overwhelming, but steady and soothing, a reminder that the universe is richer, deeper, and more fluid than it first appears. As you continue to rest within this quiet unfolding of ideas, the nature of time begins to feel less like a strict sequence, and more like something that gently bends, stretches, and adapts depending on where you are in the universe. Near a black hole, this flexibility becomes almost poetic. One of the most fascinating truths is that relativity does not just affect time and light independently. It weaves them together into a shared experience. What you see, how you perceive motion, and how you experience duration all become interconnected in subtle ways. If you were orbiting a black hole at a safe distance, you might begin to notice that the outside universe appears to speed up slightly compared to your own experience. Distant stars might seem to age faster. Events far away might unfold more quickly than expected. This is the inverse of what a distant observer would see when looking at you. From their perspective, you are the one slowing down. This mutual difference in perception is not a contradiction. It is a reflection of how space-time adjusts itself depending on position and motion. Another quiet truth is that motion itself contributes to time dilation. Even without strong gravity, moving at very high speeds causes time to slow down relative to a stationary observer. This effect, also predicted by relativity, has been confirmed through precise experiments involving fast-moving particles and highly accurate clocks. Near a black hole, both effects, gravity and motion, combine. Objects orbiting close to the black hole must move at extremely high speeds to maintain their orbit. This means they experience both gravitational time dilation and velocity-based time dilation at the same time. Together, these effects deepen the separation between different observers' experiences of time. There is also something deeply calming in how consistent these rules are. No matter where you go in the universe, the principles of relativity apply in the same way. The equations that describe these effects remain steady, even in the most extreme environments. This consistency provides a kind of quiet reassurance that even in places as unfamiliar as the region near a black hole, there is still order. Another fascinating aspect of relativity near a black hole is how it shapes what is visible. If you were looking outward while close to the event horizon, the light from the universe would appear increasingly concentrated into a smaller region of the sky. This effect, sometimes called relativistic beaming, causes light from many directions to be focused into a forward-facing view. At the same time, the rest of the sky would appear darker, as fewer light paths reach your position from those directions. This creates a kind of tunnel-like visual effect, where the universe seems compressed into a glowing region ahead of you. And yet, despite this distortion, the laws governing light remain unchanged. Light still travels along the paths allowed by space-time. It is just that those paths are no longer what we are used to. Another subtle truth is that while relativity allows for extreme time differences, it does not allow for contradictions. Even though two observers may disagree on how much time has passed, they will always agree on the fundamental sequence of events. Cause still leads to effect. The structure of reality remains intact. This ensures that, even in the most unusual conditions, the universe does not become chaotic or inconsistent. There is also a quiet elegance in how relativity preserves the speed of light as a constant, that no matter how strong the gravity or how fast the motion, light always travels at the same speed locally. What changes is not the speed itself, but how time and space are measured. This constancy acts as a kind of anchor within the shifting fabric of space-time. Another fascinating truth is how these effects influence the way black holes appear from afar. Because of time dilation and gravitational redshift, matter falling into a black hole appears to slow down and fade as it approaches the event horizon. To a distant observer, it never quite disappears. It simply becomes dimmer and more stretched over time. This creates the illusion that black holes are surrounded by a kind of frozen boundary, where incoming matter lingers indefinitely. But as you now understand, this is only one perspective. From the point of view of the falling matter, the journey continues smoothly inward. This duality, where two perspectives coexist without contradiction, is one of the most beautiful aspects of relativity. It shows that reality is not limited to a single viewpoint. Instead, it is shaped by the relationships between observers, each experiencing the universe in their own consistent way. As your thoughts begin to slow even further, there is something deeply soothing about this idea. Time is not something that rushes you forward without pause. It can stretch. It can slow. It can adapt to the environment around you. In the presence of a black hole, time itself becomes gentle, elongated, almost still from certain perspectives. And light, too, becomes more than just illumination. It becomes a guide, tracing the curves of space-time, revealing the hidden structure of the universe. Together, time and light create a kind of quiet illusion, not one that deceives, but one that invites deeper understanding. An illusion that shows us that what we perceive is only part of a larger, more flexible reality. And perhaps that is the most calming truth of all, that the universe is not rigid or fixed. It is dynamic, responsive, and quietly harmonious. Even in the presence of something as extreme as a black hole, there is no chaos in the fundamental laws, only variation, only perspective, only the gentle bending of time and light into new forms. As you settle into this thought, you might begin to feel a sense of stillness. A sense that time itself can slow, soften, and stretch, just as your thoughts do now. And in that stillness, the universe continues, calm, consistent, and quietly infinite. Chapter 6. The Sound of Silence. What falling into a black hole feels like. There is a natural question that arises when thinking about black holes, one that feels both curious and deeply human. What would it actually feel like to fall into one? Not in a dramatic or frightening way, but in a calm, observational sense. If you could approach a black hole safely, protected from immediate harm, what would the experience be like as you drift closer and closer toward that invisible boundary? The answer, perhaps surprisingly, begins not with chaos, but with quiet. One of the most important truths is that space itself is silent. Sound, as we know it, requires a medium like air or water to travel through. In the near vacuum around a black hole, there is no such medium. So even as matter swirls, as energy flows, and as gravity exerts its immense pull, there is no sound in the way we normally understand it, only silence. And in that silence, your experience would be shaped not by noise, but by sensation, by motion, and by the gentle, continuous pull of gravity. At a safe distance from a black hole, everything would feel normal. You could orbit it just as planets orbit stars, provided your distance and speed were balanced correctly. This leads to a calming truth. Black holes are not inherently destructive at a distance. Their gravitational influence follows the same laws as any other object with mass. It is only as you move closer that the experience begins to change. Another fascinating truth is that you would not immediately feel a sudden pull as you approach the event horizon. Gravity increases gradually, not abruptly. The closer you get, the stronger it becomes, but always in a continuous way. If the black hole is very large, a supermassive one, The difference in gravitational pull between your head and your feet at the event horizon could be very small. In this case, you might cross the event horizon without feeling anything unusual at that exact moment. No sudden shift. No visible line. Just a quiet continuation of your motion inward. This is one of the most counterintuitive aspects of black holes. The most significant boundary in the universe can be crossed without any immediate physical signal. But as you continue inward, deeper into the black hole, the effects begin to grow. This is where tidal forces become important. Tidal forces arise because gravity pulls more strongly on objects that are closer to the source of gravity. If your feet are closer to the black hole than your head, they will experience a slightly stronger pull. At first, this difference is small, barely noticeable. But as you move closer to the center, the difference increases. Gradually, your body would begin to stretch. Not suddenly, not violently, but slowly at first. A gentle elongation as gravity pulls more strongly on one end than the other. This process, often referred to as spaghettification, is simply the natural result of tidal forces acting over a distance. For smaller black holes, this effect becomes strong very quickly, even before reaching the event horizon. For larger black holes, it becomes significant only deeper inside. This leads to another subtle truth. The experience of falling into a black hole depends greatly on its size. In a supermassive black hole, the journey toward the event horizon could feel calm and uneventful. In a smaller one, the stretching effects would become noticeable much sooner. There is also a visual aspect to this experience. As you fall inward, the light from the outside universe begins to change. Because of gravitational lensing, light from distant stars would bend around the black hole, creating distorted and curved images. The sky would appear warped, as if space itself were gently reshaping the paths of light. Stars might appear in unexpected places. Some might seem brighter or more concentrated, while others fade from view. At the same time, the region behind you, the direction from which you came, would begin to shrink visually as light from that direction becomes harder to reach you. This creates a kind of narrowing view of the universe, where everything outside appears to compress into a smaller and smaller region of the sky. And yet, despite these changes, there is no sudden darkness at the event horizon. The darkness lies ahead, not at the boundary. Another quiet truth is that your perception of time would remain normal to you. Even as an outside observer sees your motion slow down, you would feel time passing as it always has. Your thoughts, your awareness, your sense of duration would remain steady. This creates a gentle contrast between internal experience and external observation. There is also something deeply calming in the idea that, up to a certain point, the journey is not chaotic. It is not a sudden fall, but a smooth progression. A continuous movement inward, guided by gravity. No abrupt transitions. No sharp edges. Just a gradual deepening. As you imagine this, the experience begins to feel less like falling into something unknown and more like drifting into a region where the rules slowly change. Another fascinating truth is that once you cross the event horizon, all possible paths forward lead inward. This is not because of a force pushing you, but because of the structure of space-time itself. Just as time moves forward and cannot be reversed, your motion within the black hole becomes directed toward the center. There is no way to stop or turn around, not because of effort or lack of strength, but because of how reality is shaped in that region. And yet, this inevitability does not feel urgent. From your perspective, there is still time. There is still motion. There is still a sense of progression. As your thoughts begin to slow, there is something surprisingly peaceful about this description. The absence of sound, the gradual change in sensation, the steady, uninterrupted flow inward. It is not a chaotic plunge. It is a quiet journey. Point one, where each moment follows naturally from the last, without sudden disruption. And in that quiet, the universe reveals another of its deeper truths. that even in the most extreme environments, there can be a kind of calm, a kind of stillness, a kind of silence that holds everything together. As the quiet inward journey continues, something subtle begins to change, not just in what you might feel, but in how the universe around you appears to exist. There is still no sound, no rushing wind, no echo of motion, only the steady awareness of movement through a region where gravity quietly reshapes everything. One of the most fascinating truths about this deeper stage of the journey is how your connection to the outside universe begins to fade. Not suddenly, but gradually. Light from distant stars still reaches you for a time, but it becomes increasingly distorted. Because of the intense curvature of space-time, light that once traveled in straight lines now bends in complex paths. Some of it circles the black hole before reaching you, arriving from directions that no longer make intuitive sense. The sky would not disappear, it would transform. Stars might appear stretched into arcs or clustered into bright, compressed regions. The familiar patterns of constellations would dissolve into something more fluid, shaped by gravity rather than distance. Another quiet truth is that as you move deeper, the outside universe appears to speed up. Events far away, stars moving, galaxies shifting, would seem to unfold more quickly than usual. This is another effect of gravitational time dilation, but now experienced from your perspective. Time outside is moving faster relative to you. In a sense, you are moving into a region where your personal experience of time becomes increasingly isolated from the rest of the universe. And yet, within your own frame of reference, everything still feels steady. Your thoughts remain continuous. Your awareness remains calm. There is no sudden acceleration of your own time, only the quiet realization that the outside world is changing in ways that feel distant and detached. Another fascinating aspect is how direction begins to lose its usual meaning in everyday life. Directions like up and down are defined by gravity. But near a black hole, especially deep within it, these distinctions begin to blur. Gravity no longer pulls you toward a surface. It pulls you toward a point, the singularity. And as you move closer, all paths begin to align toward that center. This creates a kind of geometric simplicity, and no matter which way you try to move, every path leads inward. This is not a force pushing you, but a property of space-time itself, guiding all motion toward the same destination. Another quiet truth is that, even as tidal forces increase, the process remains continuous. There is no sudden threshold where everything changes at once. Instead, the stretching effect becomes gradually stronger, more noticeable over time. For a large black hole, this change might still feel slow and progressive. For a smaller one, it would become intense more quickly. But in either case, the transition is smooth, not abrupt. There is also something deeply interesting about how information behaves during this journey. From the outside, it appears as though anything falling into a black hole becomes frozen at the event horizon, never quite disappearing. But from your perspective, you have already crossed that boundary and moved far beyond it. This creates a kind of separation between perspectives, a gentle reminder that reality can be experienced in different ways without contradiction. Both views are valid, shaped by position and motion. Another subtle truth is that, as you approach the singularity, the amount of time remaining becomes finite. And no matter how large the black hole is, once inside the event horizon, the journey toward the center takes a limited amount of proper time. This is not something you would feel as a countdown, but it is a property of the space-time you are moving through. Every moment carries you closer, not through force, but through inevitability. And yet, even this inevitability does not feel rushed. From your perspective, each moment unfolds normally. There is still time to observe, to think, to simply exist within the experience. Another fascinating detail is how the concept of distance becomes less meaningful. As space-time curves more strongly, the idea of measuring how far you are from the center becomes less straightforward. Distances shrink in ways that are difficult to describe using everyday intuition. What matters more is the progression of time, how your journey continues from one moment to the next. There is also a quiet beauty in how consistent the laws of physics remain, even here. Despite the extreme conditions, the underlying principles do not break suddenly. They stretch, they adapt, they reveal new behaviors, but they do not collapse into chaos. This consistency is what allows us to describe and understand these environments, even if only partially. As your thoughts begin to soften further, imagine this final stage not as something dramatic, but as something increasingly still. The outside universe fades from view. The distortions of light become more pronounced, then less relevant. The sense of direction narrows into a single path inward, and through it all, there is no sound and no disruption. Only the quiet continuation of your journey. There is something deeply calming in that silence, a reminder that, even in the most extreme places in the universe, there can be a kind of order, a kind of peace. Not the peace of familiarity, but the peace of consistency. The knowledge that everything follows from the same underlying principles, no matter how far you travel. And as you rest within that idea, the experience of falling into a black hole becomes less about fear and more about understanding. A quiet exploration of how reality behaves when pushed to its limits. A gentle unfolding of truths that are always present, but rarely so clearly revealed. And somewhere, far beyond what can be seen or returned from, the journey continues, silent, steady, and complete. Chapter 7. Feeding Giants. Accretion disks and cosmic consumption. There is a common image people carry when they think of black holes, a dark opening in space, pulling everything inward in a sudden and unstoppable rush. But the reality, as it often is in the universe, is far quieter and far more graceful. Before anything ever crosses the event horizon, before matter disappears into that unseen boundary, there is a long and intricate process that unfolds. A slow gathering, a gentle spiral, a quiet transformation of motion into light. This process forms what is known as an accretion disk. Imagine a cloud of gas drifting through space, or perhaps a star that has wandered a little too close. As this matter begins to feel the pull of a black hole, it does not fall straight inward. Instead, it starts to orbit. This happens because most objects in space already carry some motion, some sideways velocity. And rather than canceling out, this motion combines with gravity to create a curved path. The result is a spiral. Matter circles the black hole again and again, each orbit bringing it slightly closer than the last. And as it does, something remarkable begins to happen. The material in the disk starts to interact with itself. Gas particles collide, friction builds, energy is transferred, and slowly, almost gently, the disk begins to heat up. This leads to one of the most beautiful and unexpected truths about black holes. Some of the brightest objects in the universe are created not by stars, but by matter falling into black holes. As the accretion disk heats up, it begins to glow. At first, the light may be faint in infrared or visible wavelengths, but as the temperature rises, reaching millions of degrees, the disk emits powerful X-rays, becoming intensely luminous. In some cases, this light can outshine entire galaxies, and yet, the black hole itself remains dark. This contrast is quietly striking. A region of absolute darkness, surrounded by a ring of extraordinary brightness. Another fascinating truth is that accretion disks are not perfectly smooth or uniform. They are dynamic, constantly shifting systems. Turbulence within the disk creates patterns of motion, eddies, waves, and instabilities that ripple through the gas. Magnetic fields also play a crucial role. guiding the movement of charged particles and helping to transfer angular momentum outward. This outward transfer allows matter to move inward, gradually losing the energy that keeps it in orbit. Without this process, matter would remain in stable orbits indefinitely, never falling into the black hole. So, in a quiet and indirect way, the disk organizes itself, allowing matter to slowly spiral inward over time. Another subtle truth is that the inner regions of the accretion disk move incredibly fast. Close to the black hole, the orbital speeds can approach a significant fraction of the speed of light. This creates additional effects such as relativistic beaming and Doppler shifts, which influence how the light from the disk appears to distant observers. Parts of the disk moving toward us appear brighter, while parts moving away appear dimmer. This creates an uneven glow, an asymmetry that reflects the motion of matter at extreme speeds. There is also a fascinating boundary within the accretion disk known as the innermost stable circular orbit. Inside this region, stable orbits are no longer possible. Matter that crosses this threshold quickly plunges inward, no longer able to maintain its circular path. This marks the final stage of the disk's influence. Beyond this point, the journey becomes more direct, more inevitable. Another quiet truth is that not all black holes have visible accretion disks. Many exist in isolation with little or no surrounding matter. These black holes are almost completely invisible, revealing themselves only through their gravitational effects. But when matter is present, the transformation is extraordinary. Something cold and diffuse, a cloud of gas, becomes hot, bright, and structured. Energy that was once spread out becomes concentrated and visible. There is also something deeply calming in the rhythm of this process. Matter does not rush inward all at once. It takes time that it orbits, gradually losing energy, slowly moving closer. Each rotation brings it nearer, but never suddenly. This slow progression creates a sense of continuity, a gentle unfolding rather than a dramatic fall. Another fascinating aspect is how accretion disks can form in different environments in binary systems. Where a black hole orbits a companion star, material from the star can be pulled toward the black hole, forming a persistent disk. In galactic centers, vast amounts of gas can accumulate, feeding supermassive black holes over long periods. In both cases, the underlying process remains the same: motion, interaction, and gradual inward flow. There is also a quiet connection between accretion disks and the larger structure of the universe. The same principles, gravity, motion, energy transfer, apply on many scales. From the formation of planetary systems to the growth of galaxies, similar processes of rotation and gradual accumulation shape the cosmos. In this way, the accretion disk is not an isolated phenomenon. It is part of a broader pattern, a recurring theme in the universe. As your thoughts begin to slow, imagine the disk not as something chaotic, but as something fluid and continuous, a glowing spiral, gently turning, matter flowing inward, energy radiating outward. No sudden changes, no abrupt transitions, just a steady, luminous dance around a silent center, and at that center, the black hole remains, unseen, unchanged, quietly guiding the motion of everything around it. As the slow spiral of the accretion disk continues, something even more subtle begins to reveal itself. The idea that this glowing structure is not just feeding the black hole, but also shaping the space around it in quiet and far-reaching ways. The disk is not simply a passive flow of matter. It is an active system, filled with motion, interaction, and energy exchange. And within this system, one of the most striking phenomena begins to emerge. From the regions closest to the black hole, narrow streams of energy can be launched outward, straight, focused, and incredibly powerful. These are known as relativistic jets. They extend far beyond the accretion disk, sometimes stretching thousands of light years into space. And yet, despite their scale and intensity, They originate from a process that is almost delicate in its mechanics. As matter spirals inward, magnetic fields become twisted and amplified. These fields can channel some of the energy away from the disk, directing it outward along the black hole's axis of rotation. The result is a pair of jets, one extending above the disk and one below. What makes this even more fascinating is that these jets do not come from inside the black hole. They are generated in the region just outside the event horizon, where gravity, motion, and magnetism interact in complex but consistent ways. Another quiet truth is that these jets are incredibly efficient at carrying energy. They can transport vast amounts of power across enormous distances, influencing regions of space far beyond the immediate surroundings of the black hole and galaxies with active central black holes. These jets can shape the distribution of gas, heat, interstellar material, and even affect the formation of stars. Once again, the black hole reveals itself not just as a consumer, but as a participant in a larger system. Another fascinating aspect is how stable these accretion disks can be over time. While they are dynamic and ever-changing on smaller scales, the overall structure of a disk can persist for long periods, especially in systems where there is a steady supply of matter. This creates a kind of long-lasting balance, a continuous flow inward, matched by the release of energy outward. It is not a static system, but it is not chaotic either. It is a flow, a cycle, a steady exchange between gravity and motion. There is also a subtle beauty in how energy is transformed within the disk. As matter moves inward, gravitational potential energy is converted into heat and radiation. This is one of the most efficient energy conversion processes known in the universe. In fact, matter falling into a black hole can release more energy than nuclear fusion, the process that powers stars. And yet, this immense energy does not feel violent when you consider the timescales involved. It unfolds gradually, over countless orbits, through small interactions that build over time. Another quiet truth is that the brightness of an accretion disk can vary. Sometimes the flow of matter increases, causing the disk to become brighter. At other times, the supply decreases and the disk dims. These variations can happen over different timescales, from days to years to much longer periods. To observers, this creates a sense of rhythm, a pattern of activity and calm. Even in its most energetic states, the system remains governed by consistent physical laws. There is also an interesting connection between accretion disks and the spin of black holes. As matter falls inward, it can transfer angular momentum to the black hole, causing it to rotate more rapidly. Over time, this can lead to black holes spinning at very high rates. And this rotation, in turn, affects the structure of the surrounding space-time, influencing how matter moves and how energy is extracted. This creates a feedback loop, a quiet interplay between the black hole and the disk that surrounds it. Another fascinating detail is that accretion disks are not limited to black holes alone. Similar structures form around young stars, where gas and dust gather to create planetary systems. The same principles, rotation, friction, and gradual inward movement, apply across vastly different scales. This reveals a deeper truth about the universe. The processes that shape the most extreme objects are often the same processes that shape the most familiar ones. The difference lies in scale, not in principle. There is also something deeply calming in how the accretion disk maintains its structure despite the complexity within it. Turbulence, magnetic fields, and high-energy interactions all occur simultaneously, yet the overall form remains. A disk, a spiral, a steady inward flow. It is a reminder that complexity does not always lead to disorder. Sometimes, it leads to balance as your thoughts begin to slow. Imagine the accretion disk not as a place of chaos, but as a luminous current, flowing, turning, and gradually evolving, each particle of gas following its path, each orbit bringing it closer to the center, each interaction contributing to the glow that surrounds the black hole. And, beyond the disk, The jets extend outward, carrying energy into the vastness of space. A quiet exchange between inward pull and outward release. There is no rush in this process, no sudden collapse. Only motion, continuous and steady. And at the center of it all, the black hole remains, silent, unchanged, quietly shaping everything around it. As you settle into this image, there is a sense of calm in the balance. A reminder that even in the presence of immense forces, the universe can move with grace, with rhythm, with a kind of quiet harmony that unfolds over time. Chapter 8: Echoes of Collisions. Black hole mergers and gravitational waves, far out in the quiet darkness of the universe, where galaxies drift slowly and stars move in long, patient arcs. There are moments when two invisible objects begin a gradual approach toward one another. Not with urgency, not with sudden motion, but with a steady, almost unnoticeable pull. These objects are black holes. And when two black holes find themselves bound by gravity, they begin a process that is both powerful and surprisingly calm when viewed across the vast scales of time. They begin to orbit. At first, their separation may be immense. They circle one another at great distances, taking years, centuries, even millions of years to complete a single orbit. But as time passes, something subtle begins to happen. Their orbit shrinks. Not because of friction in the traditional sense, there is no air or resistance in space, but because they are losing energy in a very different way. They are radiating it outward, in the form of ripples in spacetime itself. These ripples are known as gravitational waves, first predicted by Albert Einstein as part of his theory of general relativity. For a long time, these waves remained purely theoretical, gentle disturbances that were too small to detect with existing technology. But the universe, patient as it is, continued to produce them. And eventually, we learned how to listen. In 2015, scientists working with the LIGO Scientific Collaboration made the first direct detection of gravitational waves, confirming a prediction that had stood for nearly a century. These waves came from the merger of two black holes more than 1 billion light-years away. And what they revealed was both profound and quietly beautiful. As the two black holes spiraled closer together, their motion became faster and tighter. The gravitational waves they emitted grew stronger and more frequent, creating a rising pattern, often described as a chirp. In the data, this was not sound in the traditional sense, but it was a signal that could be translated into something we could hear. A brief, rising tone, marking the final moments of the merger. And then, in an instant, the two black holes became one. But even this instant is something that unfolds gently when viewed from the right perspective. There is no explosion in the way we might imagine. No burst of light or debris. Black hole mergers are, in many ways, among the quietest of cosmic events. They release enormous amounts of energy, sometimes more than all the stars in the observable universe combined, for a brief moment, but almost all of it is carried away by gravitational waves. Invisible, silent, traveling across the universe at the speed of light. Another fascinating truth is that these waves do not move through space in the usual way. They are not vibrations within space. They are vibrations of space. They stretch and compress spacetime itself as they pass, altering distances by incredibly small amounts, so small, in fact, that detecting them requires instruments capable of measuring changes smaller than the width of a proton. And yet, despite their subtlety, these waves carry detailed information about the events that created them. From their patterns, scientists can determine the masses of the black holes, their spin, their distance, and even the way they move just before merging. It is as if the universe leaves behind a quiet record of its most dramatic transformations. Another calming truth is that these mergers are not rare. They happen throughout the universe, continuously, though most are far too distant for us to detect easily. At any given moment, somewhere in the cosmos, two black holes are slowly spiraling toward one another, their motion generating waves that will travel across space for billions of years. Some of those waves may eventually pass through our own region of the universe, gently stretching and compressing space for a brief moment before continuing on. And we would never feel them. Their effect is far too small to notice directly. But with the right instruments, we can observe them. We can listen. There is also something deeply peaceful in how predictable this process is. Once two black holes are bound together, their fate is set. They will continue to lose energy through gravitational waves. Their orbit will continue to shrink, and eventually, they will merge. Not through sudden force, but through gradual change. A slow tightening of their dance. Another fascinating aspect is what happens just before the final merger. As the black holes draw very close, they begin to orbit each other at incredible speeds, fractions of the speed of light. Their motion becomes so rapid that the final few orbits occur in less than a second. And yet, even in this rapid phase, the process remains smooth. The equations describing their motion continue to hold. The waves they produce remain consistent with our understanding of relativity. There is no breakdown. No chaos. Only a deepening of the same patterns that began when they were far apart. As your thoughts begin to slow, imagine this entire process not as a collision, but as a convergence. Point two. Paths becoming 1.2 objects, each shaped by their own history, coming together in a final, unified state. And as they do, they send out a quiet signal, ripples that carry their story across the universe. A story not told in light or sound, but in the gentle movement of space-time itself. As the final moments of a black hole merger unfold, something remarkable begins to happen. Not in the form of light or visible motion, but in the quiet reshaping of space-time itself. The two black holes, once separate, now orbit so closely that their identities begin to blur. Their gravitational fields intertwine, their paths tighten, and their motion accelerates into a rapid, final spiral. And then, almost gently, they become one. This moment is often called the ring-down phase. After the merger, the newly formed black hole is not immediately stable, carries the imprint of the collision, distortions in its shape that gradually smooth out over time. These distortions create a final series of gravitational waves, like the fading vibrations of a bell that has just been struck. The waves diminish, the motion settles, and the black hole returns to a stable, quiet state. Another fascinating truth is that the final black hole formed from a merger is slightly less massive than the sum of the two original black holes. This may seem surprising at first, but the missing mass has not disappeared. It has been converted into energy, carried away by gravitational waves. This is a direct expression of the relationship described by Albert Einstein in his famous equation, which shows that mass and energy are deeply connected. In some mergers, the amount of energy released in gravitational waves is equivalent to several times the mass of the sun, all converted into pure energy in a fraction of a second. And yet, despite this immense release, there is no explosion of light. No visible flare, only the quiet passage of waves through space-time. Another subtle truth is that these waves travel unchanged across vast distances. They are not easily absorbed or scattered. They move through the universe almost undisturbed, carrying with them the exact imprint of the event that created them. This makes gravitational waves a powerful tool for understanding the universe. They allow us to observe events that would otherwise be completely invisible. Black holes do not emit light, but through gravitational waves, they reveal themselves. There is also something deeply calming in how these signals reach us. The waves that were first detected by the LIGO scientific collaboration had traveled for over 1 billion years before arriving on Earth. For all that time, they moved steadily through space, unaffected by stars, galaxies, or cosmic dust. And then, for a brief moment, They pass through our planet, stretching and compressing space by an amount so small it could only be detected with the most sensitive instruments ever built. A quiet arrival. A gentle signal. Another fascinating aspect is that black hole mergers are not the only sources of gravitational waves. Collisions between neutron stars, the remnants of massive stars, can also produce these ripples. In some cases, these events do produce light bursts of gamma rays and visible radiation, allowing scientists to observe the same event through multiple forms of information. But black hole mergers remain uniquely silent in terms of light. They speak only through space-time itself. There is also a growing network of observatories around the world and in space, working together to detect these waves. In addition to LIGO, projects like Virgo and Cagra contribute to this effort, improving our ability to locate and understand these distant events. Together, they form a kind of listening system, a way of sensing the universe through its most subtle movements. Another quiet truth is that as our detection methods improve, we are beginning to observe more and more of these mergers. Each detection adds to our understanding, revealing patterns and properties that were once hidden. We are learning how common these events are, how black holes form and grow, and how they interact over time. And yet, even with this growing knowledge, there is still a sense of calm mystery. Each signal is brief. Each event is distant. Each story is carried across the universe in silence. There is also something deeply poetic about the idea that the universe can be heard in this way, not through sound waves, but through the motion of space-time itself. It suggests that the cosmos is not just a visual experience, but a dynamic one, filled with patterns and rhythms that extend beyond what we can see. As your thoughts begin to soften, imagine these waves moving through space, not rushing, not colliding, just traveling, steady and uninterrupted, passing through galaxies, through empty regions of space, through everything, carrying with them the quiet memory of distant events, and somewhere, far beyond what we can observe directly, more mergers are happening. More black holes are spiraling together. More waves are being created. Each one a gentle echo of a transformation that has already taken place. And as those waves continue their journey, they become part of the larger story of the universe, a story not written in words or images, but in motion, in rhythm, in the subtle, continuous shaping of space-time itself. And in that quiet motion, there is a sense of stillness, a reminder that even the most powerful events can unfold without noise, without disruption, only with a gentle, steady presence that moves outward and continues on. Chapter 9. The Fading Giants, Hawking Radiation and Black Hole Death. There is a quiet assumption that often settles in when we think about black holes, that once they are formed, they last forever. Endless, unchanging, eternal. But the universe, in its subtle and patient way, tells a different story. Even black holes, the most stable and enduring objects we know, are not truly permanent. They change slowly, almost imperceptibly, over spans of time so vast that they feel more like stillness than motion. And at the center of this transformation is one of the most fascinating ideas in modern physics, introduced by Stephen Hawking. The idea that black holes are not completely black, that they emit radiation, and that, over time, they can fade. This concept, known as Hawking radiation, begins not inside the black hole, but just outside the event horizon. To understand it, you can imagine the vacuum of space not as empty, but as something quietly active, a field where tiny fluctuations constantly occur. In quantum physics, pairs of particles can spontaneously appear and disappear in extremely short periods of time. These are known as virtual particles, and under normal conditions, they annihilate each other almost immediately. But near the event horizon of a black hole, something unusual can happen. If a pair of particles forms just at the edge, It is possible for one particle to fall into the black hole while the other escapes into space, to an outside observer. It appears as though the black hole is emitting particles, a slow, steady release of energy. Another quiet truth is that this process reduces the mass of the black hole. The particle that falls inward carries negative energy relative to the outside universe, effectively decreasing the black hole's total mass. The particle that escapes becomes real, carrying energy away. And over time, this leads to a gradual loss of mass. This is not something that happens quickly. For large black holes, the rate of radiation is incredibly small. A black hole with the mass of the Sun would take far longer than the current age of the universe to lose a noticeable amount of mass. And supermassive black holes, like those at the centers of galaxies, would take even longer, trillions upon trillions of years. This leads to a calming realization. Black holes are incredibly stable over timescales that far exceed anything we experience. Their fading is not a rapid process. It is a slow, almost gentle drift toward change. Another fascinating truth is that the temperature of a black hole is related to its size. Smaller black holes are actually hotter than larger ones. This might seem counterintuitive at first, but it reflects the way Hawking radiation works. As a black hole loses mass, it becomes smaller, and as it becomes smaller, its temperature increases. This creates a kind of feedback loop. The smaller the black hole becomes, the faster it radiates energy. The faster it radiates energy, the quicker it loses mass. And as this process continues, it accelerates. But for most of a black hole's existence, especially for large ones, this acceleration is so slow that it is almost unnoticeable. Another subtle truth is that Hawking radiation connects two very different areas of physics. It combines ideas from quantum mechanics, describing particle behavior on the smallest scales, with general relativity, which describes gravity and the structure of space-time. This makes it one of the first and most important steps toward understanding how these two frameworks might work together. And yet, despite its significance, Hawking radiation has not yet been directly observed. The effect is simply too small for current instruments to detect in astrophysical black holes. But it remains a widely accepted prediction, supported by strong theoretical foundations. There is also something deeply poetic about the idea that black holes, which absorb everything that crosses their event horizons, can slowly give something back. Not in the form of the same matter that fell in, but as energy, radiation that spreads out into the universe. A quiet return. Another fascinating aspect is what happens at the very end of a black hole's life. As it becomes extremely small and hot, the rate of radiation increases dramatically. In the final stages, it may release a burst of energy, a brief, intense phase where the remaining mass is converted into radiation. This is sometimes imagined as a kind of final flash, but this moment occurs after an unimaginable span of time. By the time a black hole reaches this stage, the universe itself will be very different. Stars will have burned out. Galaxies will have evolved beyond recognition. The cosmic background will have cooled even further. And in that distant future, these final moments of black holes will unfold quietly, scattered across an aging universe. Another calming truth is that this process ensures that nothing in the universe is truly permanent. Everything changes. Everything evolves. Even the most stable structures eventually transform. And yet, this change is not chaotic. It follows consistent laws. It unfolds gradually. It maintains a kind of quiet order. As your thoughts begin to slow, imagine a black hole not as something fixed and unchanging, but as something that exists within time, participating in the long story of the universe. For most of its existence, it remains steady, dark, silent, and stable. But slowly, almost imperceptibly, it begins to fade. Not in a dramatic way, not with urgency, but with a gentle release of energy, a quiet shift from presence to absence. And in that slow fading, The black hole becomes part of the larger rhythm of the cosmos, a reminder that even the deepest darkness is not beyond change. As the idea settles in that even black holes slowly fade over time, something deeper begins to emerge. The universe, in its quiet consistency, does not allow even the most extreme objects to remain unchanged forever. Instead, everything participates in a long, gentle transformation. And in the case of black holes, this transformation unfolds through the steady whisper of Hawking radiation. One of the most fascinating truths is how incredibly slow this process is for large black holes. A stellar mass black hole, formed from the collapse of a massive star, would take on the order of years to fully evaporate. To place this into perspective, the current age of the universe is about years. This means that black holes live for timescales so vast that they stretch far beyond any familiar measure of time. Supermassive black holes, the giants at the centers of galaxies, last even longer. Their lifetimes can extend to years or more. These numbers are so large that they are less like durations and more like distant horizons of time, concepts that can be gently appreciated rather than fully grasped. Another quiet truth is that during most of this lifespan, the black hole changes very little. The rate of Hawking radiation is so small that the black hole remains almost perfectly stable, continues to exist as a steady presence in the universe, influencing its surroundings through gravity while very slowly losing mass. This creates a sense of calm continuity. For billions, trillions, and far beyond, the black hole simply persists. Only in the final stages does the process begin to accelerate. As the black hole shrinks, its temperature rises. This increase in temperature leads to more radiation, which in turn reduces its mass more quickly. The feedback becomes stronger. The fading becomes faster, and yet, even this acceleration follows a smooth and predictable pattern. There is no sudden disruption, only a gradual intensification. Another fascinating aspect is the nature of the radiation itself. Hawking radiation is not made up of the same particles that originally fell into the black hole. Instead, it consists of a mix of particles determined by the black hole's temperature. This raises one of the most profound questions in physics. What happens to the information about everything that has fallen into the black hole? If the black hole eventually disappears, and the radiation does not carry clear information about its contents, does that information vanish? This question is known as the black hole information paradox. It touches on one of the deepest principles in physics, that information should not be destroyed. Over the years, many ideas have been proposed to resolve this paradox. Some suggest that the information is somehow encoded in the radiation, though in a highly scrambled form. Others propose that the information is stored on the event horizon itself, like a kind of cosmic surface memory. There are even ideas that the information remains preserved in subtle correlations within the radiation, waiting to be decoded. While the full answer is still being explored, this question reveals something important. Black holes are not just objects of gravity. They are gateways to deeper understanding. Another quiet truth is that the final evaporation of a black hole represents a kind of return. The mass that once formed the black hole, gathered from stars, gas, and other matter, is gradually released back into the universe's energy. Not in its original form, but transformed. This transformation reflects a broader pattern in the universe. Nothing is truly lost. It changes. Form. It moves from one state to another. It participates in a larger cycle. There is also something deeply calming in the idea of such long timescales. The universe is not in a hurry. Processes unfold at their own pace, guided by consistent laws. Black holes do not rush toward their end. They fade, slowly, patiently, and in that patience, there is a kind of stillness. Another fascinating detail is that in the far future, when most stars have burned out and galaxies have grown dim, black holes may become some of the last remaining active objects. They will continue to emit Hawking radiation, quietly releasing energy into an increasingly cold and empty universe. In this distant era, the universe will be very different from what it is today. But even then, the same principles will apply. The same gentle processes will continue. There is also a subtle beauty in how the story of a black hole comes full circle. It begins with the collapse of a star. Matter coming together under gravity. It exists as a stable, quiet presence, holding that matter in a compact form. And it ends with the gradual release of energy back into the universe. A cycle of gathering, holding, and releasing. As your thoughts begin to slow, imagine this entire lifespan not as something distant or abstract, but as part of a continuous flow. A black hole forming in the quiet aftermath of a star's life, persisting through vast stretches of time, and eventually fading, returning its energy to the cosmos. There is no abrupt ending. No sudden disappearance. Only a gradual transition. A soft conclusion to a long and steady existence. And in that gentle fading, there is a sense of completion. A reminder that even the most enduring things are part of a larger story, one that continues quietly and endlessly. Chapter 10: The Deepest Mysteries, Information Paradox and Beyond. As everything begins to slow, as the vast ideas of time, gravity, and quiet transformation settle into stillness, we arrive at one of the deepest and most delicate mysteries surrounding black holes. Not a mystery of motion, not a mystery of force, but a mystery of information. At first, this may seem like an abstract idea. Information does not feel as tangible as matter or energy. But in physics, information is something fundamental. It describes the exact state of a system, the arrangement of particles, the structure of energy, the details that define what something is. And one of the most important principles in modern physics is that information is never truly lost. It can change form, can become difficult to access, but it is not supposed to disappear completely. And yet, black holes seem to challenge this idea. When something crosses the event horizon, all information about it appears to vanish from the observable universe. The details of its structure, its motion, its history, all of it becomes hidden behind that boundary. And if the black hole eventually evaporates through Hawking radiation, as proposed by Stephen Hawking, then what happens to that information? Does it simply cease to exist? Or is it preserved in some way that we do not yet fully understand? This question is known as the black hole information paradox. And it is not just a small puzzle. It sits at the intersection of two of the most successful theories. In physics, on one side, there is quantum mechanics, which insists that information must be preserved. On the other, there is general relativity, developed by Albert Einstein, which describes black holes as regions where information can be hidden from the outside world. Both theories are incredibly accurate in their own domains. And yet, when brought together in the context of black holes, they seem to disagree. This tension has led to decades of exploration, filled with ideas that are both subtle and profound. One of the earliest suggestions was that information might be lost after all, that black holes could violate the rules of quantum mechanics. But over time, this idea became less favored, as it would require a fundamental change to one of the most well-tested frameworks in physics. Instead, many scientists began to look for ways in which information could be preserved, even if it appears hidden. One such idea is that information is encoded on the surface of the event horizon itself. This concept is closely related to what is known as the holographic principle, the idea that all the information contained within a volume of space can be described by information on its boundary. In this view, the event horizon acts like a kind of surface where information is stored, even as matter falls inward. The black hole, then, is not just a simple object, but a system with a kind of memory. Another fascinating proposal involves the nature of Hawking radiation itself. While the radiation appears random at first glance, some theories suggest that it may carry subtle correlations, patterns that encode information about what has fallen into the black hole. These patterns would be extremely difficult to detect, but they would ensure that information is not truly lost. Instead, it is transformed and spread out into the universe in a highly complex way. There are also more recent ideas that challenge our understanding of the event horizon itself. One such idea is the concept of a firewall, a hypothetical region of high-energy particles at the event horizon that could alter the behavior of information. However, this idea remains controversial, as it conflicts with other aspects of relativity. Another approach suggests that the interior and exterior descriptions of a black hole are not independent, but connected in subtle ways. An idea sometimes referred to as black hole complementarity. In this view, different observers may have different but consistent descriptions of reality, depending on their position. This echoes something we have seen before, that perspective matters, that reality can be experienced in different ways without contradiction. Another quiet truth is that these questions are not just about black holes. They touch on the fundamental nature of reality itself. How information is stored, how it evolves, how the universe maintains consistency across different scales. Black holes, in this sense, are not just objects of study. They are windows. They reveal where our current understanding reaches its limits and where new ideas begin to emerge. There is also something deeply calming in the way this mystery unfolds. It is not a problem that demands an immediate answer. It is a question that invites exploration. A quiet space in our understanding, where curiosity can rest as your thoughts begin to soften. Imagine the information carried by everything in the universe. Every particle, every wave, every interaction. All of it moving, changing, and evolving over time. And within black holes, that information is not destroyed, but hidden, transformed, and perhaps slowly released. Not lost, just beyond immediate reach. And in that idea, there is a kind of comfort. A sense that the universe is not careless with its details. That even in its most extreme environments, there is a deeper order at work. One that we are still learning to see. As this final chapter gently unfolds, the mystery of black holes begins to feel less like a problem to solve, and more like a quiet doorway into deeper understanding. The information paradox does not stand alone. It connects to a wider landscape of ideas, each one exploring how reality is structured at its most fundamental level. And as these ideas develop, something remarkable becomes clear. Black holes are not just objects in the universe. They are intersections, places where different layers of reality meet. One of the most intriguing directions this exploration has taken is the idea that space-time itself may not be as continuous as it appears. At very small scales, far beyond what we can directly observe, space and time might be made up of discrete units, like a kind of subtle fabric woven from fundamental pieces. In this view, the smooth geometry described by general relativity emerges from something deeper, more granular. And black holes, with their extreme conditions, provide a place where this deeper structure might reveal itself. Another fascinating concept is the idea that space and information are connected more closely than we once believed. Some modern theories suggest that the geometry of space-time, the way it bends and curves, may actually arise from patterns of information. This means that gravity itself could be linked to how information is distributed and organized. If this is true, then black holes are not just regions of strong gravity. They are also regions where information is highly concentrated and transformed. This perspective brings a quiet unity to different areas of physics. Gravity, quantum mechanics, and information theory begin to feel less like separate topics and more like different expressions of the same underlying reality. There is also a deeply interesting idea known as the entanglement of information. In quantum mechanics, particles can become linked in such a way that the state of one instantly relates to the state of another, no matter how far apart they are. Some researchers have proposed that similar connections might exist in the structure of spacetime itself, that distant regions could be linked through hidden relationships, forming a kind of network beneath the surface of reality. In some interpretations, this even connects to the idea of wormholes, subtle bridges between different regions of spacetime. While these ideas remain theoretical, they suggest that the universe may be far more interconnected than it appears, and black holes may be key to understanding those connections. Another quiet truth is that the study of black holes has already changed our understanding of the universe in profound ways. It has revealed that space and time are flexible, that gravity can shape the flow of time, that information may be more fundamental than we once believed. And yet, despite all this progress, there is still so much that remains unknown. There is something deeply calming in that. The realization that knowledge is not a fixed destination, but a continuous journey. That even as we learn more, new questions emerge, not as obstacles, but as invitations. Black holes, in this sense, are not mysteries to be feared. They are guides. They show us where to look next. Another fascinating idea that has emerged in recent years is that the boundary of a black hole, the event horizon, may behave like a kind of dynamic system with properties similar to temperature and entropy. Entropy in physics is a measure of the number of possible configurations a system can have. And black holes appear to have an enormous amount of entropy, suggesting that they contain vast amounts of information. This idea connects back to the work of Stephen Hawking and others who showed that black holes are not just simple objects, but thermodynamic systems with measurable properties. This blending of gravity, thermodynamics, and quantum theory is one of the most exciting areas of modern physics. It hints at a deeper framework, one that could unify our understanding of the universe. Another subtle truth is that, even as we explore these ideas, black holes remain physically distant and safe. They are not immediate threats. They exist far away, embedded within galaxies, following the same consistent laws that govern everything else. Their mystery does not come from danger, but from depth, from the way they stretch our understanding beyond its usual limits. As your thoughts begin to settle into stillness, imagine the universe not as something fully known, but as something gently unfolding, each discovery adding to the picture, each question opening new possibilities. And at the center of this unfolding, black holes remain, quiet, patient, and deeply revealing. They do not rush to give answers. They do not force understanding. They simply exist as part of the vast, intricate structure of reality. And perhaps that is the most calming truth of all, that the universe is not something we need to fully grasp all at once. It is something we can explore slowly, gently, with curiosity and calm. As you rest within this idea, the story of black holes comes to a quiet close, not as an ending, but as a pause. A moment of stillness, a place where everything you've explored, the birth of stars, the bending of time, the silence of space, the slow fading of even the darkest objects, comes together into a single quiet understanding that the universe is vast, that it is consistent, and that even its deepest mysteries unfold with a kind of gentle order. And in that order, there is peace.